Hello, I'm Taeyoon Lee. To briefly introduce myself, I've got my PhD last fall in robotics at Seoul National University under supervision of Professor Frank Park, and I'm currently working at Naval Labs robotics team as a research scientist. Before starting the talk, I would like to thank the organizers again for the kind invite to this great workshop. Now let me start the talk. My talk will be mainly about presenting how geometric methods and tools can be applied to some of the important problems in dynamic model-based robotics. And one of the primary goals of this talk is actually about making audiences really feel that these geometric approaches are not merely some fancy rigorous machinery to solve problems, perhaps in a hard way, but rather suggest better understanding of the problem at first hand. And many situations lead to very effective and practical set of tools to solve the original problem. So exploiting the physics-based models and accompanied planning and control methods have been deeply investigated in robotics for a very long time. And for industrial robots executing mostly pre-programmed motions, a good kinematic model combined with a good controller is often enough. Now, as robots are required to do more complex, interactive, and dynamic tasks, dynamic models are really starting to play a more central role in these challenging domains. Not only for planning and control, multi-body dynamic models can also be used in other applications like biomechanics or sports analysis or hardware design. And also, more recently, simulation models are not merely used as a testbed for handcrafted controllers, but they are beginning to be used more and more for generating realistic training samples for data-driven learning-based controllers. And of course, the performance of handcrafted model-based controllers, as well as controllers that are learned from simulation models, will only be as good as the accuracy of the model. And then one might ask, how accurate should the model be to solve the problem? And it turns out that there is no single simple answer to this question, but it would rather depend on the specific usage of the model or the task we wish to solve with the robot. Right? For instance, a simplified or reduced dynamic models combined with a good model-based controller are often enough for bipedal working or postural balancing of the humanoid robot. However, for robots performing a broader range of dynamic and compliant tasks, reasonably complete dynamic models are often required. Tasks involving complex whole-body manipulation while also remaining balanced, and also detecting and coping with external collisions and context. These are the examples where full-body dynamics should be considered or are desired to be considered. These days, I would like to claim that accurately identifying or estimating even the complete rigid body dynamic model is getting harder and harder. First of all, robots are becoming complex and high DOF, which generally implies that there are increasing number of parameters to identify. For example, for the case of humanoid robot, there are more than hundreds number of inertial parameters to identify. Unlike the case of fixed phase manipulators, collecting rich and complete data for a full humanoid model identification is nearly impossible to achieve in practice due to a lot of practical limitations, including safety issues. And also, as robots are coming with lightweight and low inertia estimates get more sensitive to the model mismatch and sensor noise, which leads to a much larger chance of parameters identified as physically infeasible values. For these and other reasons, in many practical situations, using only sensor data is not satisfactory for reliable full model identification of the robot. And another important feature of the model, here I would like to emphasize, is about the ability to adapt online to possible changes and disturbances. This kind of problem has long been investigated as adaptive control in the control systems field. And I feel that adaptive control is getting a renewed attention these days, as it shares very similar objectives with learning-based approaches like with reinforcement learning or online learning paradigm. And obviously, this online adaptation of model is generally a much more challenging problem than the offline counterpart. Just from the pure model parameter estimation point of view, the available data is way more scarce. And for real-time control aspect, one must deal with the effect of online model adaptation to the model-based controller in various aspects. For example, stability of the robotic system. This was a brief introduction of my talk, and the remaining would be about showing how geometric consideration of the model parameters can largely alleviate the difficulties mentioned in the previous slide. And let me start with taking a closer look into the geometric structure of the model parameter space of the robot. This is basically F equals ma dynamic equation for rigid multibody system. How is the motor torque control input applied to the joint of the robot? And the matrix M is the mass matrix. B is the nonlinear vector term containing all the nonlinear forces like Coriolis or gravity force or friction forces. And the vector phi is the collection of model parameters we wish to estimate from data. Generally, the model parameters phi include not only the mass and inertial properties of each bodies of the link, but they also include frictions and elasticity in the actuation mechanisms and many more. But throughout this talk, I would particularly focus on the geometric structure of the mass inertial parameters. But I just want to make a brief point here that the methods and geometrical approach I would describe throughout this talk are not necessarily confined to only the mass inertial parameters. As I think most of the physical objects like frictions and stiffness and even contact possess its own unique geometric structure. So let's take a closer look into the mass inertial parameters of a single rigid body first. The inertial parameters of a single rigid body constitute the mass, the center of mass, and moments of inertia. And if you count the numbers of the independent parameters, one can realize that mass inertial parameters of a single rigid body span 10-dimensional space. However, it turns out that the parameter values themselves are not actually quite sufficient to fully describe the information for the mass inertial property of a single rigid body. For instance, even if someone tells you the center of mass of the robot link is in coordinate, say 0.1, 0.2, 0.5 in space, you might have to ask back to the person in which reference frame they have measured those values, right? So clearly the space of mass inertial parameters are 10-dimensional manifold admitting infinite possible choice of coordinate choices. Right? They can be identified as a choice of body fixed reference frames and also physical units. Now we would like to define a way to measure distance between two mass inertial parameters of a single rigid body in this 10-dimensional manifold. And we would first consider standard Euclidean metric that many people may like to use for its simplicity. So here is three rigid body having the same total mass with uniform density, but only differing in their shape. And then we evaluate the mass inertial parameters of each body in the same coordinate as indicated in the slide as black Cartesian frame, D. While blue and gray ellipsoids look more alike from the red ellipsoid, the standard Euclidean metric actually says that they have the same distance among all of the ellipsoids, which mildly defies our intuition. And things get even worse when you consider different coordinate choices. Now, when one computes the same Euclidean distance, but evaluating in the green reference frame denoted as A frame in the slide, the result says that the distance between the red and gray ellipsoids is like 4 times more closer than the gray one and the blue one. So clearly, standard Euclidean metric is not a nice choice or intuitive choice of distance metric in the space of mass inertial parameters. So coming back to the original definition of mass inertial parameters of a single rigid body, we can see that they are actually the 0, first and second moment values of the underlying mass distribution of this rigid body. And it can be observed that they are not just 10-dimensional vectors, but have certain structure and correlation among them. And it turns out that this structure can be nicely captured by the matrix manifold structure. And it has been shown in the recent paper by Professor Patrick Wensing and others that the space of physically feasible mass inertial parameters can be identified as a 4x4 symmetric positive definite matrix manifold. And in this particular matrix manifold, one can impose a well-defined, a coordinate-invariant dimensionless Riemannian distance metric that better encodes the natural distance between the underlying mass distribution of two rigid bodies. Coming back to our 3-body example, using the Riemannian distance metric, the distance between the blue and gray ellipsoids is much smaller than that between the gray and red one, while the result being completely invariant to the choice of reference frames and also the choice of physical units. So now I want to show how one can exploit the geometric structure of this mass inertial parameter space to formulate the problem of estimating them from data. Again, we are considering the F equals ma form of dynamic model. And I have to say the field of robot dynamic model identification is a very long history in robotics. And nearly all of the approaches exploit the fact that model parameters are linear with respect to the dynamic equation. And the model parameters that can be linearly decomposed from the dynamics include not only mass inertial parameters, but also other parameters like joint Coulomb friction parameters. But once you construct this linear decomposed form of the dynamics, the standard next step is to collect data. So typically, robot follows some pre-planned reference trajectory in a position control mode, and you take measurements of motor torques, joint angles, velocity, and acceleration at multiple time instances. Then taking advantage of the linearity of the parameters with respect to the dynamic equations, you end up solving a big linear system of stacked equations. And we'll say it A phi equals B for simplicity. So obviously, the first thing to try would be to solve it with linear least squares method as shown in the slide. However, when you actually apply naive least squares method as presented earlier, it is quite often the case that you get negative mass or negative inertia. In other words, the previous 4x4 symmetric matrix representation of the inertial parameters of some rings can be identified to be non-positive definite value. Or even if we are considering the minimal identifiable set of parameters, it is quite often the case that one may end up with non-positive definite mass matrix. This is a very serious problem for implementing modern model-based controllers and also for dynamic simulation. This is a result of implementing the most standard trajectory tracking controller called the computed torque controller and on the AMBIDEX 7UF manipulator using the identified parameters from linear least squares method as shown in the previous slide. And you can see that due to the non-positive definiteness of the robot actually exhibit positive feedback signal and immediately diverge. And this is also experiment of identifying the mass inertial parameters of a human subject with a very low cost affordable sensor. And the identified mass distributions using a very simple linear least squares method shows very physically unrealistic results, as shown in the right in the slide. And also there are a few references actually highlighting that the performance of some of the state-of-the-art whole-body model-based controllers for humanoids can actually be sensitive to the quality of the model parameters. And obviously, if your model is correct and your sensor is completely noise-free, you should never get those physically invisible estimates. But in reality, of course, there is always an issue of model mismatch, and one has to cope with the measurement noise. This issue has been deeply investigated by many researchers for a long time. And for standard industrial robot manipulators with 6 or 7 or fewer degrees of freedom, there are various robust identification methods that are shown to work robustly against these difficulties. But again, coming back to one of our previous slides, in many situations, one can not just get sufficient amount of good quality data for reliable full model estimation. So that is, one is mostly confronted with solving a very ill-conditioned linear systems of equations, A phi equals B, for a high-dimensional robotic system. So one of the very nice thing about robotics problems is that most of the things we are working with are physical values, right? And they're not actually the parameters of arbitrary functional approximators like neural networks. And one can easily obtain good initial estimate for physical values like mass inertial parameters from the CAD model or datasheet, or even through rough guess. So a very simple and effective method to robustify your parameter estimation problem is to regularize the problem using the prior estimate and balance your parameter fit between the noisy, incomplete sensor data and your complete or error-prone prior estimate. So once you have both your A phi equals B equation from the sensor data and the prior estimate ready, you can simply reformulate the least squares identification problem to the following regularized form of least squares problem. And here is some distance metric function d between the estimation parameters we wish to estimate. The corresponding prior values will act as a penalty term or so-called regularizer. And one of the main finding is that actually the choice of distance metric matters a lot in obtaining a reliable and sample efficient solution to the problem. And we have shown that using geometric coordinate-invariant distance function to this regularized formulation leads to a much more robust and physically plausible solution with much less data. So in cases where the measurements are insufficient to reliably identify the full set of parameters, this regularization metric can improve the generalizability of the result by more naturally capturing the prior on the underlying mass distribution of the bodies, rather than simply numeric values of the parameters. So I won't go into the too much details, but one of the major drawbacks of geometric computational algorithms is that the corresponding optimization problems usually are inherently non-convex and lead to very computationally intensive to solve. Because one of the core reason is that normally geodesic distances, the Riemannian distance between two points in the manifold, are not a convex function. So to cope with this problem, we also propose a convex formulation under the same coordinate-invariant Riemannian geometric framework that directly addresses this computational problem. So our convex formulation leads to a globally optimal solution with reduced computation fast and reliable convergence. And also, importantly, easy inclusion of additional convex constraints to the primary. The main idea behind our approach is proposing a divergence measure that provides a convex second-order approximation to the original Riemannian distance, while still retaining the desired coordinate invariance properties. So in our paper, we have done quite a large set of experiments to demonstrate the effectiveness of our approach. So I will not go to all the experiments, but the main takeaway is that our geometric approach compared to the vector space counterpart leads to a much more sample efficient and a generalizable solution. So we've done experiment on the manipulator, AMBIDEX manipulator, and also Log-det robot, MIT Cheetah robot. This additional simulation experiment, and also the human experiment. So now let's talk about robot adaptive control. When you see the learning capability of humans, you see that the humans normally do not learn from scratch in every single task we are confronted with, right? So for instance, if someone masters to drive a car, so it is likely that they can drive in any places in the world with a fair amount of practice. And we adapt online to new situations based on the past or recent experience. So adaptive control is a subfield of control engineering where the objective is to control the plant without knowing dynamics or the parameters of the dynamic model. It is different from the robust control methods where one wishes to design a fixed controller that is guaranteed to work within a predefined uncertainty bound on the dynamics model. But adaptive control rather takes the approach of explicitly adapting the model or model parameters online that is fitted back to the model-based controller. So it is in part more close to the online learning ability, just like humans naturally have. So technically speaking, due to the online nature of the problem, one has to design the parameter adaptation law and the controller in a joint manner that would eventually achieve a desired performance of the robot. So robot adaptive control had been very popular in the 80s and the early 90s, and two of the most popular and successful adaptive trajectory jerking control algorithms are called adaptive computator control proposed by Craig, Su, and Sastry, and passivity-based adaptive control proposed by Slotin and Lee. These two algorithms are built upon the theory of Lyapunov analysis. So one first defines Lyapunov function cantonade as the sum of trajectory tracking error and the primary estimation error. And loosely speaking, one then come up with both the controller and the primary adaptation law that guarantees the Lyapunov function to be a non-decreasing function with respect to the time. So this eventually ensures the tracking error to be asymptotically converged towards zero. And the conventional choice of parameter error related Lyapunov function cantonade, BP, indicated in the slide, is normally defined as the weighted quadratic error, quadratic parameter error. So here the weight matrix gamma has to be predefined as arbitrary positive definite matrix. Then it turns out that one can derive the following form of adaptation law, where the parameter update is defined as the gradient of some error-like function times the constant inverse gain matrix gamma. And what the continuous time Lyapunov theory tells is that this adaptation law should work for any choice of matrix gamma. But in practice, with a naive choice of gain matrix gamma, one gets a very numerically unstable result with a bad convergence of the tracking error. So in our paper, we have actually done a simulation experiment trying using a scaled identity matrix for gamma. And we could see a very unstable and unpredictable behavior of the robot, which defies the original theoretical result. And it is to note here that in simulation, we added no additional noise to the dynamics or the feedback signal. Actually, it turns out that this unstable online behavior of the robot turns out to be more related to the unstable phenomena we observe in fixed-step gradient-based numerical optimization. So in continuous time domain, the steepest the steepest gradient flow is guaranteed to converge exactly toward the local minimum solution. But if this was the end of the story, right, then there is nearly no problem left to solve in numerical optimization. So actually, in discrete time implementation of gradient-based optimization, the choice of weighting matrix gamma here that appropriately scales or precondition the gradient values matters a lot in order to effectively iterate and converge toward the optimal solution. For instance, in the second order Newton's method, the matrix gamma is chosen as the Hessian of the cost function. And it turns out that replacing the matrix gamma with the state-dependent Riemannian metric on the Riemannian manifold of the parameter space is to a much faster and stable convergence in robot adaptive control. And this type of gradient-based update is known as a natural gradient update law in the literature. And natural gradient is a coordinate invariant and leads to a faster convergence and respects the underlying geometry of the parameter space. This adaptation law no longer needs to adjust a full adaptation gain matrix gamma, but we just need to tune a single step size, small gamma. So the theory behind is that one can also rigorously demonstrate the stability of this new geometric update law using the same Lyapunov stability analysis. So this is done by simply replacing the original quadratic parameter error Lyapunov function candidate with the divergence measure we presented in the earlier slide. And I would like to note that the method here is not just confined to the case of mass inertial parameters, but this can be straightforwardly extended to the parameters that reside in general convex affine manifolds. And also, this can be further extended to robust adaptation laws involving non-smooth switching parameter update. So we have done experiment on the real robot AMBIDEX, and we could show that this gain tuning free natural gradient based adaptation law works remarkably well in practice. And you can see that the natural gradient based adaptive control, as shown in the very right side of the video, quickly adapts and converges toward the reference motion as seen in the right side, as seen in the left side of the video. This is the last technical part of my talk, which is about optimizing the trajectory samples for use in model parameter estimation and identification. As I mentioned earlier, real-world data in robotics is not cheap. So collecting data, we have to physically run the robot. And in many cases, we don't want our expensive robots to fall over and break while collecting data before even testing our algorithm with the data. So coping with this problem by coming up with robust algorithm that works with bad quality data is one solution, but these solutions in nature is in many cases biased toward, for example, the prior belief on the model parameter or specific assumptions we make to simplify the problem. So there is a whole branch of field that addresses the problem of carefully selecting the optimal collection of data samples under many practical constraints associated with the hardware limitations and safety issues. So this is referred to as many different names in different fields. So it's referred to as experimental design in statistics, active learning in machine learning community, and optimal excitation problem in control systems field. The most standard formulation is to minimize the expected mean variance of the parameter estimate or maximize the information with respect to the trajectory sample subject to the constraint. So the objective function of this optimization problem should represent some meaningful measure of information or equivalently the uncertainty over the estimation parameter. So again, I don't want to go into too much details here, but the key takeaway is that in order to construct a well-defined invariant measure of information over the multivariate parameters residing in a manifold, one should again consider the geometry of the underlying parameters. And we can actually reformulate the set of classical criteria of information in a geometric way and obtain more reliable results that is completely invariant to the choice of coordinates, lead to the optimization of better behaved and more physically meaningful codes of that represent more meaningful measure of information. And before closing the talk, I would like to make a brief comment on my own personal view on recent progress in some of the recent progress in robot learning. So it's also alluded throughout the talk. I feel that control engineers and machine learning engineers have long been solving quite similar problems, but in different names, right? But one of the big differences, I guess, is about what kind of mathematical or physical object or variables we are considering to solve or describe the problem at hand. So one of the nice property of physics-based models that roboticists are comfortable with is that we can fully exploit the very rich structure of the data, parameters or variables that are associated with the task. And I do feel that a lot of interesting and inherent properties of data and objects that are prevalent in robotics problems are yet quite underexploited in learning-based control approaches. And we should note that often the things that we work with are not vectors, but the elements of the manifold. So to conclude my talk, it is hoped that the coordinate-invariant geometric view on robot modeling and control methods described in this talk can be helpful in addressing and solving more challenging problems upcoming in robotics. Now, I would like to introduce our next speaker, Professor Bruno Adorno. He has earned bachelor and master's degree from University of Brasilia and finished his PhD from University of Montpellier. He's now currently associate professor at the Federal University of Minas Gerais, and his research interest lies both in practical and theoretical aspects related to robot kinematics, dynamics, and control, with application to mobile manipulators, humanoids, and also cooperative manipulation systems. Today, he will give a talk about complex robotic systems, modeling, control, and planning using dual quaternion algebra. This work has been recently released as a software package based on dual quaternion algebra, and it is featured in this year's IEEE Robotics and Automation magazine. Now let's welcome Professor Bruno Adorno. Thanks.